And so here's what I want you to remember, that the work that we're doing in here is skill-based, which means what I want is for you to be able to do all of the stuff that I'm about to do. And some of you can. Some of you already have it. Some of you will be able to do it as soon as you see me. It's gonna like all click in and make sense. Others of you might need to do a little bit of practice. In general, I don't assign homework. Don't have you doing a whole lot. I don't ask you to do a whole lot outside of class, but this may be a time, and I don't think it's unreasonable for this to be the case every once in a while. This may be a time when you need to do some work and thinking outside of class. Maybe even come in here and take some measurements. So it starts with this. We had discussed the idea that impulse is an application of force, overall force, on an object that lasts some amount of time. So we used, oops, that's not at all something I can write with. We used the symbol J for impulse, and what we said is that's equal to the average force, overall force, acting on an object, times the amount of time that force is being applied. And then we had our scenario that we were thinking about was a scenario in which we figured momentum is going to be conserved. There's going to be conservation of momentum here. We had two carts on a level track, no other forces besides the force of the collision between the carts. And what we were wondering is, okay, well we know that for each cart, its impulse should also be equal to its change in momentum. So if we look at like one cart at a time, the impulse acting on one cart will be equal to the change in momentum of that cart. And then we had this conversation where we worked out that because momentum is conserved, it seemed reasonable that there was going to be some connection between the impulse on one cart and the impulse on another cart and the change in momentum on another cart. And we couldn't quite nail it down. We couldn't quite figure out, well, what is it going to be? Because we thought, well, maybe it's the same, and maybe it is the same. But we couldn't, aside from our intuitive thinking that it makes sense for these two things to be the same because momentum is conserved. So we didn't get any further than something like this. So what I suggested is, well, if we have two carts and we collect some data, we can look at the impulse acting on one of those carts, and we can look at the change in momentum of the other one, and we'll get some values like we could graph potentially. And if we were to do that, then we should see, if we were to graph it this way, for example, we'll have the impulse acting on one cart on our y-axis, the change in momentum acting on another cart on the x-axis, and then we might see some relationship. And we didn't know what it was going to be, but there was going to be some potential interpretation of that graph. What I then told you is, if we want to measure impulse, we need to be able to calculate the average force acting on a cart and the amount of time over which that force is occurring. We can do that with the supercarts. They have a force sensor, and the computer has a really accurate clock. So we can do this using graphical analysis. If we want to look at change in momentum, that's going to be, m2 v2 prime minus m2 v2, an object's final momentum minus its initial momentum. Mass, we can measure with a balance, but if we use supercarts, we know what the mass of these things are. It's about 0.3, 0.29, 0.285. And we can measure velocity with the supercarts as well. So we can make these measurements by hooking up the carts to graphical analysis and collecting some data. So let's do that. And what I'm going to do is, I'm just going to do one round of this, but in order to get a trend, we would need to collect data multiple times. and I did already. You should have already as well, but I did already. I collected data last year, and then I collected some more data this morning. So we'll see what this looks like. This morning, the data that I collected, I had this yellow cart. There were no masses on it, and I think what I did. So the green cart was heavier, and I think what I did is I moved the yellow cart pretty fast and the green cart kind of slow. But I'm going to change everything up, and you know why? Because it doesn't matter. As long as we have essentially the parameters that we laid out, conservation of momentum is probably going to hold in this situation. It doesn't matter which cart we measure force on, which cart we measure momentum on. It doesn't matter what their masses are, what their velocities are. We could look at a whole bunch of different collisions. If there's some connection, we should still see it even in an entirely different scenario. So let's do that. So I'm going to show you the whole thing from start to finish, just in case you missed it. And this is part of the skill that I'd like you to be able to have. I would like you to be able to do this work that I'm about to show you. So the first thing is we're going to collect data from the carts. And I have two carts here, and I think they're so when I connect them, I only need to measure force on one of them. And I only need to measure velocity for the other one. And the way that I have these set up, it doesn't matter which color is which, it doesn't matter which one you use, but I happen to have a bumper on my green cart. So I'm going to measure force with my green cart, and that means with the yellow cart, I'm going to measure velocity. So my yellow cart, I want my sensor channel to be position, that's correct. My green cart, it wouldn't hurt to measure position, but I don't need it. So I'm going to turn that off and just measure force, because that'll make it easier for me to keep track of what's going on. And then the information I need is force, which I've got here, and velocity. So I don't need 3 graphs, I just need 2. I need to measure force on my green cart. You probably can't see this, but that's what's showing here. And I want to measure velocity on my yellow cart, and that's what's showing here. And then right now, again, you probably can't see this, but it's telling me that the force on the green cart is 1.7 or so newtons. But there's nothing pushing or pulling on this. So I'm going to zero that. This should be telling me that there's no force acting on it at all, and now there isn't. When I push on the bumper, it gives me a negative force. That matters. Impulse has a direction, because force has a direction. So the impulse on this cart could be this way, or it could be this way. On the green cart, if I have impulse this way, I would expect its momentum to change in this direction. Its momentum will become more to your left. And so that's what I'm going to expect to see. Oh, thank you. Hang on to me. I'm so sorry. Yep.
You're far down the alphabet.
Yep. Oh my goodness, he's not here.
I know the table.
Okay. Right. Yeah. Okay.
I don't understand this guy.
Wow. This is.
I actually do not understand this guy.
Okay, I'm so sorry.
Couldn't tell you the impulse is.
So this is in G45. So those of you who don't know where G45 is, it's the room right across from Mr. Mock's room, and next to the bathroom. And if you don't know where it is, wait for somebody else who does.
Bye.
If you don't know the answer, just
Good luck.
it's not.
And this is required, not by me, but by somebody.
By someone in the Normandy district.
Okay, sorry about that. So now all I need to do is have the carts collide and collect data. So again, part of what I want you to be able to do is this part. it's not enough for you to be able to just multiply some numbers together, which I know you could do. I want you to be able to actually get the data. So when I click collect here, can I make this bigger? I wonder, oh, look at that. If I click collect here, and then I'm gonna move looks like the yellow one I think was moving quite a bit faster than the green one to start with, and I don't like that. I don't like this right here. That's not, I'm not satisfied with that. I think, I don't know exactly what happened, but I don't love it. So I'm gonna collect another round, because the velocity should be constant at first. So let's try that again. It's really, yeah, I think it's hitting a, well, that's all right. We're gonna just roll with this, and it's not gonna be perfect, and that's okay. All right, well so this is pretty good. This is a little odd. It looks like it's accelerating. No, it's slowing down. That's good. I think we're good. I think we got good data here. So the first thing I'm gonna do is I'm gonna get force data. I'm gonna zoom in on this because I want the average force from the time the collision started until the time that it ended. I don't wanna find the average force over a longer period of time than that, because then I'm just gonna get a bunch of zeros as part of my average. So looks like the collision started here and ended about here. And so if I go to statistics, it tells me that my average force, I'm just gonna jot it down over here, my average force was about negative 1.5 about. So my average force was about negative 1.5, and the amount of time was about 0.22 seconds. And remember, the negative sign matters. There was negative impulse being applied to that cart. And now I'm going to look at the change in velocity, which I'll be able to use to find the change in momentum. So my velocity before the collision was about negative 0.53. So my initial velocity was about negative 0.53. My final velocity was still negative. It was still moving in the negative direction, but it was moving more slowly. And it was moving at about negative 0.22. So my final velocity was negative 0.22 meters per second. And I know how much this cart weighs. The cart is about 0.3. Each of these bars is about 0.5. So this is about 1.3 kilograms. So with that information, I can do the calculations that I was talking about. I can find the impulse, because I have average force and time. I can find the change in momentum. What I'm gonna do though is I'm gonna have a computer do this for me, because that's how I would do it in real life. This part isn't something that I expect you to be able to do, but I will say it's a super handy skill to have. So I'm gonna put my data into this Excel spreadsheet that I made a while ago, and these 7 trials were ones that I did last year in my physics classes. I did a bunch of them in different classes, and then this one here, this is from this morning in the first period physics class. And so my new trial, my mass of the cart that I looked at the velocity was about 1.3. Its initial velocity was negative 0.53, and the final velocity was negative 0.22. And it calculates the change in momentum for me. It was about 0.4. And for the force, my force was about negative 1.5, that was on the other cart, and the amount of time was about 0.22 seconds. So that's about negative 0.33 is my impulse acting on that other cart. And I did something weird here. I didn't call them cart 1 and cart 2, or cart A and cart B, or yellow and green. I called one cart Q and one cart 17. And I did that because one of the things that happened was that students felt like, well, you're always supposed to do the same thing with cart 1. So there's always a cart 1 and there's always a cart 2. And a cart 1 is like a this kind of cart, an impulse cart, and cart 2 is a velocity cart. And if you don't do it that way, you've messed it up. But that's not true. You just need to find impulse acting on one cart or thing. It doesn't even have to be a cart. You can measure force and the amount of time that that force is exerted on some other object, knock yourself out. And then you need to measure the change in velocity and mass for the other thing. It doesn't matter what you call them. You don't have to have one green and one yellow. You don't have to have one that's called cart 1. It's all the same information no matter how you do it. And when you look at my change in momentum and the impulse acting on the other cart, it's not easy to see a pattern here. I can't see one, in fact. I'm looking at this and I don't visually see a pattern. The numbers aren't the same. The only thing is these are all positive and these are all negative, but I'm not sure what that's going to look like. So I'm going to go back to my suggestion, which is, what if we plot the data? If I want to know what the relationship between these two numbers is, I can probably find it by looking at a graph. So again, there's a computer piece here that you don't have to know, but if you're good at Google Sheets or Excel, it actually will potentially save you a bunch of time. Hang on. That's not what I wanted to do. I want my change in momentum. Okay. So I have 9 trials now, and then my impulse. So this is the change in momentum of one of my carts. This is the impulse acting on the other one, and you can see, like, now I can see there, like, it's this one on the right is always, the magnitude is a little bit less, but I still am not seeing a pattern. So I'm going to let the computer do it for me. I'm going to put a chart in, and then I'm going to add a trend line and the equation. And what I get is this equation right here. So I'm going to, I don't know if I can copy that or not. Can I copy that? Oh yeah, look at that. Okay, so what it looks like here is the impulse is equal to this stuff. So, so let's take a look at that in this context. So what we're saying is the impulse is equal to this stuff. Well, my x variable is the change in momentum of cart 2. And the impulse that I measured was the impulse of my first cart, my in this case, the green cart. So what I'm seeing here is that it looks like this is my relationship. But let's think about it, because we said we think that these things might sort of be like the same, and this isn't the same, but actually this is really close to -1. So maybe it looks something like this. And this number right here, 0.0162, is awfully close to 0. This right here is darn close to this equation. The relationship that we uncovered is almost that the impulse acting on my green card was equal to the opposite of the change in momentum of the yellow card. And that, in fact, makes a lot of sense. And I'm going to show you a couple derivations for that right now. So part 1 of what I want you to be able to do is collect data. Part 2 of what I want you to be able to do is make a graph and interpret the data. You can make the graph by hand, or you could make it using a computer, it doesn't matter. But being able to make that graph is pretty important. And then part 3, and this was all in the lab itself. Part 3 was, okay, well, why does this make sense? And what I suggested is it makes sense for 2 reasons. We can think about this in 2 separate ways. We're going to get the same thing either way, so I'm going to show you both. Okay? So if we think about this in terms of conservation of momentum, then we have our typical scenario where we have 2 objects that are, in this case, I had them both rolling toward each other, and after the collision, they were moving in different directions. And I think this one just kept moving in the same direction or something. I don't know. It doesn't matter. But basically, like, this is the general framework of conservation of momentum. And what we decided is that the total momentum of our system, of our system before the collision is gonna equal our total momentum after the collision. Alright? So the momentum of one of my carts plus the momentum of the other one before the collision should equal the momentum of the first one plus the momentum of the second one after the collision. And if I want to think about this in terms of change in momentum is final minus initial momentum. And I can do that, I can find the change for either one of these carts, right? So if let's say I subtract M2V2 from both sides, I now have here the change in momentum for my second cart, final minus initial. And then, if I subtract M1 V1 prime from both sides, I have M1 V1 minus M1 V1 prime, which is the opposite of cart 1's change in momentum. Cart 1's change in momentum would be this minus this, so -1 times the change in momentum will give me this term right here. That's going to be equal to the change in momentum for cart 2. We see that change in momentum should be equal and opposite. But remember, impulse applied to something will equal its change in momentum. So this will be the same as the opposite of the impulse applied to cart 1. That's going to be equal to the change in momentum of cart 2. We can flip the negative sign around and we get what we just saw. The impulse acting on one cart should be equal to the opposite of the change in momentum of the second cart. And this is a mathematical derivation that explains the data that we just saw. We can look at this in another way as well. The second way to look at it is by applying Newton's third law. Newton's third law says that the forces acting on an object will always come in pairs. So in this case, we have one cart here and one cart here. At the moment of the collision, this cart is experiencing a force in this direction from the other one. And this cart is experiencing a force in this direction from the first one. So this is the force from cart 2 on cart 1. This is the force from cart 1 on cart 2. That force isn't static, it changes. It starts small, and it gets bigger, and then it gets smaller again, the magnitude of the force. But Newton's third law says that when there's a force between objects, that force will always have the same magnitude. It will occur at the same time, and it will be opposite in direction. So we know that at any given time, these two forces will be equal and opposite. They have to be. If we were to make a graph of these two forces, what we'd see is, oh, that's funny, that's not what I meant to do. What we'd see is the force acting on this cart is in the positive direction. It's going to start small, get larger, and then get small again. The force acting on this cart is in the negative direction, but it's going to start small, get larger, and then get small again, and its magnitude will always be the same as the force acting on the first cart. So these two graphs show the forces acting on both of these carts. The average force for each of these carts will then also have the same magnitude, right? But they're going to have opposite signs. So the average force acting on this cart will be negative in direction, but equal to the magnitude of the average force acting on this cart, which will be in the positive direction. This axis down here is our time axis. So the amount of time that goes by during which these forces are occurring is the same for both carts. So that means that the impulse acting on this cart right here is going to be equal and opposite to the impulse acting on this card here. They will have the same force, average force, they'll have the same time, the magnitude of the average force will be the same, the time is the same. The only thing different is gonna be the direction of that force. The magnitude for both of these cards of the impulse is gonna be our average force times time. One of them will have impulse in the negative direction, this one. The other will have an equal amount of impulse in the positive direction, this one. And again, since we know mathematically impulse is going to tell us the amount of change in momentum, this is going to be equal to the change in momentum of the second object. So the opposite of the impulse acting on that second object will be the opposite of its change in momentum. So again, we've arrived at the same hypothesized relationship, which matches what we saw in our data. So there's a lot here to think about, and again, what I want to remind you is that what I'm looking for is for you to be able to do this stuff. It's not to just know this, because now everybody does and everybody could write it down. What I would ask you to consider is, if I were to walk up to you right now and say, here, take these two cards, do a collision, find the impulse acting on one of them and the resulting change in momentum of another one. Could you do it? Could you do it without your pals? Could you do it on your own in some reasonable amount of time? The second thing is, if I said, okay, now I want you to tease out the relationship between those two quantities. So collect data a bunch of times and make a graph. Could you do that? You don't have to have the ability to put equations into Google Sheets like this, but you should be able to generate a graph like this, either in a spreadsheet or by hand, so that you can then draw a trend line and look at the slope of the trend line. And then lastly, could you explain why this makes sense? It's not just a matter of parroting back what I said, but could you explain it to somebody who didn't understand? There's a bunch of students who just left because they had to take a test. If those students come back, how confident are you that you personally could sit with them and say, oh, well, here's what's going on. We know that these two quantities have to be equal and opposite because Newton's third law and because conservation of momentum. So that's the degree to which I would like you to have facility with this stuff. Okay, so we are going to take. We're gonna take a working break now. I'm going to pause for a second and.